this is the solutions for the practice exam number 1. So number 1 is nothing more than unit conversions. So if I want 2 power converters in total, and I want to get that to Womp Rat Tails, I got to figure out all the different conversions along the way that we're going to have to do. Okay? So the first one that we can go to is the sentence directly before. You can trade 3.5 power converters for every 6 speeder engines. So for 6 speeds, we get 3.5 power converters. Okay? If we go to the sentence before that, then we see that 2 speeder engines are equivalent to 5 protocol droids. So there's 5 pros in every 2 speeds. If we go to the one before that, then we see that 1 protocol droid is the same as 1.5 synthetic couplers. So 1.5 synthetic couplers is the same as 1 pro. We need another one which says that 2 blaster pistols are worth 4 synthetic couplers. And last but not least, 20 Womp Rat Tail is worth 3 blaster pistols. So, if we take a look at this, power converters cancels power converters, speeds cancels speeds, protocols, protocols, synthesis, synthesis, blasters, blasters. The only thing left with is Womp Tails, so we plug this into our calculator and blast away. Okay, moving on to number 2. Okay, what are the 4 fundamental forces of nature? This we went over in class, namely that we have gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. And we know that this is the weakest, and as we go this way, we get more and more until we have the strong nuclear force. And again, how do we explain this? We know that gravity can overcome the electromagnetic force can overcome gravity because you can hold things up. The weak nuclear force can overcome electromagnetism because it keeps the electrons out of the protons, and the strong force keeps the protons in the nucleus, and we call it a day. For part C, we say that while reading the driver's ed manual, right, we know that it takes us 10 meters to stop for a certain braking power of -A. This problem we did exactly on one of the homeworks, except I think I just changed the numbers around a little bit. But if I triple my initial speed, how much further would it take you to stop? So in case A, or in the original case, right, we know that equation 5 says that V final squared is equal to V initial squared plus 2a delta x. And the nice thing about this is that they tell us delta x, they tell us minus a, they tell us 2. We know V initial squared, or at least we can get this in terms of V initial squared. And we know that V final squared is 0. Okay? So, I should actually say that V initial squared is the thing that we want to actually manipulate here. Because we want to know, if we tripled our initial speed, how much further would it take us to stop? So let's solve this for V initial squared. Okay? We see then that V initial squared, since V final squared is 0, will be 2a delta x. So, if we triple, then the new V initial is going to be 3 of the other V initial, which means that when we plug this into the above equation, we'll have 3 V initial squared is equal to 2a delta x. This is the same as saying 9v initial squared is equal to 2a delta x. Well, we know that the v initial squared is the same as that we had before. The 2 in the a is the same, and we know delta x. So, what we're basically saying is that by tripling this, we are getting a factor of 9 times. Problem number 3. A box containing a small toy is hung from a ceiling at rest and attached to a frictionless track. This is the one that was missing a diagram, but the diagram looks like this, that we're pulling with a force as such, and it's hanging along a frictionless track like this. Okay? The boy runs for 2 seconds, and the box accelerates at 2 meters per second squared. The first thing that we ask is, what is the force required to make the box move as described by the above? This is our 5-step process for Newton's laws. So the first step is that we draw a free body diagram. So we do that. And we see that we have the force of gravity pulling down. We have the applied force pulling like this, which we know has both an x and, in green, and y component. That's step one. Step two is write out Newton's laws. So we sum the forces in the x direction is equal to mass times acceleration in the x. Sum the force in the y, and that's equal to mass times acceleration in the y. Step three says take the forces from the free body diagram and plug them into the left-hand side. So upon doing that, in the x direction, we have the applied force, x is equal to mass times acceleration in the x. And for the y direction, we have gravity, and I should do this in a different color. We have the applied force in the y coming down, so it gets a negative, and a minus force due to gravity coming down. And technically speaking, this is making contact, okay, so there is a normal force as well. But I'll just leave that out for the moment because it's irrelevant for this problem. And this is equal to negative m times acceleration in the y. Now we apply the physics, which we know that acceleration in the y has got to be 0 because the box is not flying off of the floor or anything like this, or off of the ceiling. Okay, and we know that the applied force in the x, and this angle was supposed to be given as 35 degrees, and the mass is given as 10 kilograms. So this is going to be the magnitude of the applied force times the cosine of the angle. The applied force in the y is the magnitude of the applied force times the sine of the angle. So we plug these into our equations just like we did in class. And the first equation becomes magnitude of the force times the cosine of the angle is equal to mass times acceleration in the x. That's the one that we need. We know the acceleration, we know the mass, we know the angle. We can solve this for the applied force. So the applied force then, or the magnitude of the applied force, is just the mass times the acceleration in the x divided by the cosine of the angle, which gives 24.4 newtons. And we have it. Part B, if after 2 seconds the toy falls out of the box towards the floor, how long will the toy be in the air? Well, we have to acknowledge at this point that this is nothing more than just a free fall problem. Okay, so if we want to know how long is this in the air, well, we need to know how high this thing is suspended. And again, this was included in the diagram, which was didn't get attached to the practice exam, and I apologize for that. Okay, this height was supposed to be 10 meters, and so if we know that this is 10 meters, right, then we know that it's going to fall 10 meters. We can use equation 4, which says that y final is y initial plus v initial in the y times t minus 1/2 gt squared. And v initial in the y is 0 if it falls from rest, at least in the y direction. Y final is 0, and y initial we know is 10. So if we plug this in, then we see that the time is nothing more than the square root of 2y initial divided by g, which is 2 times 10 divided by 9.8. This thing is in the air for just 2 seconds. I'm sorry, I forgot to take the square root. This thing is 1.2 seconds. Now we go on to the next section. Oh, I'm sorry, I almost forgot part C. What is the velocity right before it strikes the ground? Well, for that we can use equation 3 is probably the easiest. That v final is v initial minus gt, because we now know the time. V initial is still 0, so v final is just negative 9.8 meters per second squared times 1.4, which is 13.8 meters per second. And we have everything for question 3. Problem 4. For problem 4, we have a stone thrown off a building only in the y direction. The building is 100 meters tall. So y initial is 100. Y final is 0. We know that the acceleration in the y is negative g. And we don't know its initial velocity. And we definitely don't know its final velocity either. And that's what we want to find. Okay? But we do know the time that it hits the ground is 3 seconds. So for the first thing that we can do is we can find the initial velocity by using equation 4. That tells us that y final is y initial plus v initial in the y times t minus 1/2 gt squared. And we solve this for v initial, just like we did on a few of the homework problems from 2 homeworks ago. So if we do the algebra out, and we recognize that y final is 0, then we're going to move all the relevant terms over, and what we get is v initial in the y is going to be 1/2 gt squared minus y initial, whole thing divided by time. And if we plug in our numbers, we are left with a negative 18.6 meters per second, which should make sense to you that in order to get down that far, that fast, you had to throw the stone downward, hence the negative. Once we have the v initial, then solving for the v final is no problem because we can just use equation 3 or equation 5. But equation 3 will get us there quickest, no pun intended, ho yeah. So v final in the y is v initial in the y minus gt. And if we use this to just plug in our numbers for v final y, we get overall a negative 48 meters per second. So this thing is cooking when it gets to the bottom. Now we go on to the longer ones. Problem 5. Okay, one of my fantastic dreams that I'm in the Super Bowl, but what am I doing? I'm going to make a kick of the football, okay, and I'm shooting at a goalpost over here, okay, and in this problem, I tell you that x initial is 0 and x final is 61 meters, and I also tell you that the y initial is 0 and the y final, if I'm going to make the kick, is going to be 10 meters. And for this one, what we want is the magnitude of v initial and the angle of v initial, right? And that's, again, that's this vector here, right? And this angle is what I want. So this is very similar to some of the ones from the previous homework, whether it's the kangaroo jumping or the soccer ball problem. It's basically the soccer ball problem in disguise. So let's go over this, how we're going to do it. We're going to analyze the x motion and y motion, solve one equation for one, and plug it into the other, okay? So let's do it. If we start with the x motion, and we use equation 4 for the x, we know that x final is x initial plus v initial in the x times t. And I'm leaving out the acceleration because we know that the acceleration in the x is always 0 because we ignore air resistance, right? And I remind you that v initial in the x is magnitude of v initial times the cosine of the angle. V initial in the y is the magnitude of v initial times the sine of the angle as per our vector rules. So this is equation 4, which can be simplified to just being magnitude of v initial times the cosine of the angle times t. Now, just like how we had in class, we don't know vi and we don't know cosine theta, so it's up to you which one you want to solve this for. To be honest, to make our lives as easy as possible, would solve this first for the magnitude of vi. That tells us that the magnitude of v initial is nothing more than x final divided by t cos theta. And we're going to use that into the y equation, again, equation 4, which says that y final is equal to y initial plus v initial y times t minus 1/2 gt squared. And everywhere there is a magnitude of v initial, we're going to plug it in. But remember, that's hidden in this term right here, because this is actually y final is magnitude of v initial times sine of theta times t minus 1/2 gt squared. And now I plug this in the place where I underlined in green. And we go to it. I'm going to do that down over here. So I get y final is equal to x final divided by t cos theta times sine theta times t. And that's nice because we're going to see that the t's cancel there. Minus 1/2 gt squared. And what does this really tell us? This tells us that since the t's cancel, then we can divide sine theta by cosine theta and replace that with tangent of theta. And what we have is y final is equal to x final tangent of theta minus 1/2 gt squared. We know the time, we know x final, and we know y final. So therefore, the only thing that's unknown is the angle. So I'm going to solve for the angle. Okay? Doing that quickly, that gives us y final minus 1/2 gt squared. Plus 1/2 gt squared. Whole thing divided by x final is equal to the tangent of theta. How do I get the tangent out of that? I take the inverse tangent, and so we see then that the angle that we arrive at, theta, is about 22.7 degrees. Once we have the angle, we're halfway there because we wanted the angle and the V initial. Once we have the angle, we can take this and plug it into this equation here. And if we do that, then we see that the magnitude of V initial is going to just be the 61 divided by 3.3 times the cosine of 22.7. And we plug that into our calculator, 20 meters per second, which sounds about right given the rest of the context of the problem. You okay, man? Okay, so back we're at it. Problem 6 I'm not going to bother doing because we do that exact problem in class. Okay, so we're going to jump straight to number 7. Another vector problem. Okay, we have 3 vectors, A, B, and C. The problem is that vector C is given with its magnitude and direction. So first let's find the components of C. If we do that, we know that C's x component is the same as the magnitude of C times the cosine of the angle, and C's y component is the same as the magnitude of C times the sine of the angle. And so if we plug these into our calculator, then these become 0.98 in the x direction and negative 2.00 in the y direction, which is basically 1 and 2. So we see that C then, in reality, is going to be 1 in the I hat minus 2 in the j hat. Okay, so now we have everything that we need. So for part A, it asks us to compute 2a plus 3b minus 2c. 2a, 3b minus 2c. And all we have to do is just go very slow through this. So 2a, if I plug in a, is negative I hat plus 3j hat plus 3 times b, which is 3i hat minus 4j hat minus 2 times c, which we now know is 1i hat minus 2j hat. Okay, ignore that noise in the background. That is my crazy dog Molly. And if we just knock this out, we get negative 2i hats plus 6j hats plus 9 more I hats minus 12j hats minus 2 more I hats plus 4j hats. We combine all the i's with i's and all the j's with j's. Negative 2 plus 9 minus 2 more is really 5 I hats. 6j's, negative 12j's plus 4j's is really minus 2j's. And we have the vector 2a plus 3b minus 2c. Part B, find the magnitude and direction of that vector. Okay, well, we know that in order to find the magnitude of that vector, 2a, to find the magnitude of that vector, we take the square root of its x component squared plus its y component squared, which is nothing more than the square root of 25 plus 4, which is the square root of 29, and that's good enough for an answer, or you could put it into your calculator. How do you find the angle? The angle we know is the inverse tangent of the y component divided by the x component. And if we get this out, we see that this will be a negative 21.8 degrees. And so then the question always becomes, well, how do we measure this thing? Well, take a look. If the vector is 5i hat minus 2j hat, it means that we went over 5 in the I hat and then down to j hat, which means that the vector that we're talking about is really like this, which means that the inverse tangent gave us this angle right here as 21.8 degrees. So there's plenty of ways that we can write this. We can call this 21.8 degrees south of the horizontal, or we use the standard that we agree on, which is that all angles are measured from 0, right? Which is then going to be 360 minus 21.8, which is 338. Yes, I know, Molly. 338.2 degrees. Okay. Part C, we said that you can ignore because it's the dot product. And then part D says find the angle between A and B. Well, the only way that we can do this is with a sketch, right? So if we draw out where the vector A is, right, let's just do these in a couple of different colors. Vector A is minus 1 in the I hat, plus 3 in the j hat. Right, so it looks something like this. Okay. which means that we can find its angle that I'll call theta A, and B is 3 in the I hat minus 4 in the j hat. Bad choice to put that there, but you see that theta B will be here. Okay, so if we found theta A and theta B, we can take the difference, thus finding the angle between them. How do we do that? Well, theta A, as always, is just the inverse tangent of its y component divided by its x, which is 3 divided by 1. Theta B is just the inverse tangent of its y components, which is minus 4, divided by the x component, which is 3. We put these each into our calculator, we take the difference according to that sketch, and we have our answer. Okay. Problem 8 I'm going to save to the very end of the video because it's by far the most complicated problem on here, and you're not going to have anything as difficult as that on the exam, but it is absolutely solvable. So let's move on to number 9 for the time being. Okay, number 9 is me running across the quad and trying to avoid getting hit by a water balloon. This is basically Bruce and Henrietta, except replace the word bagels with water balloon, etc., etc., etc. Okay, so what do we have? We have someone up here who's going to fire a water balloon at some unknown initial velocity, and I'm going to call that v initial of the balloon. I'm down here, and I look awesome, and I'm running with some v initial of James, which is constant. Okay, and I tell you exactly how fast I run. Okay, we know y initial is the height of the building, which in this case is 60 meters, and y final is 3 meters because it lands on my head. I'm sorry, I can't copy. That should be 2 meters. Okay, so we have y initial and we have y final. So what do we have to agree on? We have to agree that we should know, just like how we had for the bagels, that x final of James is going to be the same as x final of the water balloon in order for there to be a hit. So that's going to be our link between the two motions. But in order for us to exploit that, we first have to figure out how long the water balloon is in the air. So let's use the y motion of the balloon to get the time. Well, we're going to use that by using equation 4, which says that y final is y initial plus v initial and yt minus 1/2 gt squared. We know v initial and the y is 0 because the balloon was launched completely horizontally. We know y final, we know y initial. We can solve this then for time. Time, as per usual, is the square root of 2 delta y divided by g, which is about 3.4 seconds. Okay. So, now that we have the time, we know that's how long the water balloon was in the air, which is the same as, which is related to how long that I've been running. So, how long have I been running? Well, Nirav the Great waits 4 seconds before he fires the water balloon. Okay? So that means the total time of James running is 3.4 plus 4, which is 7.4 seconds. So, if we know my velocity, which we do, it's 3 meters per second, then x final of James is 3 meters per second multiplied by 7.4 seconds, which is 22.2 meters. That's how far I got, and that is where the water balloon has to hit me. Therefore, we can now use equation 4 for the balloon, and if we do this, then we know that x final is going to be v initial times t, because the water balloon cannot accelerate, and if we call x initial 0, we can solve this for v initial, namely v initial would be the x final of the water balloon divided by time, which is going to be 22.2 divided by the time of the balloon, which is 3.4 seconds, because that's all the balloon had in the air, which is a 6.5 meters per second. And we have it. Okay. Apparently I can't count because problem 11 comes after problem 9, because that makes a whole lot of sense. Blame the bad physics professor, in my opinion. Okay, but in this problem we have you firing an arrow with a v initial of 21 meters per second at an angle of 66 degrees. Okay, so this is one of the more straightforward ones where we know both the initial velocity and the angle, and we're going to ask a bunch of stuff about this. Part A, we're going to ask what is the max height of the arrow. And we know in these types of problems when we're talking about the max height, we want to break the motion up into two pieces, right? Namely on the way up and on the way down, because we know the max height will be right about here. Okay? And so what do we know at the max height? Well, at the max height, we know that v final of the y, not the overall v final, but v final of the y is going to be 0, right? Stay still for a very brief second. Okay? But we also know, because of our vector rules, let's just get this out of the way right now, that v initial of the y is magnitude of v initial times the sine of the angle. V initial in the x is magnitude of v initial times the cosine of the angle. And if we get values for these right away, then we get 8.5 meters per second and 19.2 meters per second respectively. Okay, so now we know the initial velocity, and so now we can just use anything that we like. I prefer, for this type of case, I prefer for us to use equation 5, because we don't know any information about the time that it took to get to max height. We could find the time, but that's up to you. I'd rather just use equation 5. Equation 5 says that if we're going to get to max height, then v final squared is equal to v initial squared minus 2g delta y. Okay, and I'm doing that for the y direction, obviously, so that v final squared would be 0. We know v initial, we know 2, we know g, we can find delta y. So we solve this for delta y. Delta y here is going to be v initial squared divided by 2g, and we see that the negative signs go away. So if we take our 19.2 and square it, and we divide it by 2 and divide it by 9.8, then we get that this is 18 meters in total, is the max height. Sorry, I used the wrong velocity on that one because my dog was bothering me. Since we're using the v initial for the y here, or the y, which we set up here was 8.5 meters per second. It should be 8.5 squared divided by 2 divided by 9.8, which tells us that this gets up to... Would you leave me alone, Molly? Okay, back after the dog debacle. I realized that I just have these literally backwards. This should be our... Oops. This should be our 19.2 meters per second. And this should be our 8.5 meters per second. I apologize for that. So I actually had it right the first time. I knew something seemed wrong there. So once again, so I take the 19.2, and I square it, and I divide it by 2, and I divide it by 9.8. And now we get the fact that we go up a net of 18.8 meters. And now I'm much happier with that answer. Okay. So now we have the net height of the arrow. Okay, so part B then says how long is the total flight of the arrow? Well, in order for us to find the total flight, well, it would help us if we actually knew the time that the arrow was in the air. So once again, if I do this with the y direction at max height, then we can use equation 3. And if we do this and we solve for the time, then we see that the time, since the v final of the y is 0, is just v initial in the y divided by g, which again, using the correct time now, is 19.2 divided by 9.8, which is going to be 1.95 seconds, so just shy of 2 seconds. Okay, so if that's the time it takes to get to the max height, well, then we know that if it took that long to go this far, it'll take the exact same amount of time to go this far. So therefore, if we multiply that number by 2, we get the total time of flight. So the time of flight is going to be 3.9 seconds. Okay, if we then ask what is the magnitude of the final velocity of the arrow, well, we know for final velocity we need two pieces. We need v final in the x and we need v final in the y. Well, v final in the x we already know because it's the same as v initial in the x because there's no acceleration, and we know that this is 8.5 meters per second. So the last thing that we need to know is what is the v final in the y. Now, just like how we said in class, well, if you're returning to the same height that you started, you will have the same velocity in the y that you started, namely v final in the y is going to be 19.2 meters per second. Well, if we then want the magnitude of v final, This is going to be the square root of its component squared, which is 19.2 squared plus 8.5 squared, and wouldn't you know it, this comes out to 21, exactly like we thought it would. Last but not least, if a cliff is 125 meters away, can the arrow make it to the cliff? Well, the arrow is in the air for 3.9 seconds. So even if we said 4 seconds, right, how far can it actually get in the x? Well, let's use the x motion, and we use equation 4. X final is x initial plus v initial in the x times t. Well, if x initial is 0, and we know v initial in the x, which is 8.5, this is 8.5 meters per second times about 4 seconds. 8.5 times 4, this is only 34 meters, which is not even close, so the answer is a giant no, frowny face. The arrow cannot get there. Ladies and gentlemen, this concludes the brief version of the answer key. You can probably pause this video at any point to see the individual steps, but I will also pull this down as a PDF so that you have it as well. If there's any typos, I apologize. If I went too fast, I apologize. But remember, this is meant for your betterment. Until I see you tomorrow in class, I hope you have a great night and never stop thinking.